Okay, in this video we're going to cover section 8.3, which deals with testing a claim about the mean x bar. And so in this section we're going to focus on a case which I've kind of avoided until now, but it's really the more realistic case. And that's the case, so we're going to focus on the case where the underlying parent population, its standard deviation is not known. And so that's kind of an interesting and realistic situation, because recall that from the central limit theorem, we know that the distribution of sample means is, as long as we have big enough sample sizes, or if we know that the underlying parent population is itself normally distributed, then the central limit theorem tells us that the distribution of x bar is normal mu, and then with a standard deviation of sigma over the square root of n. But in order for us to apply this, it assumes that we know what this sigma is. But now we're saying we don't know what sigma is. So we're going to be introduced to the t-distribution. And the t-distribution is, it's a symmetric distribution, just like the normal distribution. It'll have a bell curve. But there actually are several t-distributions, and we'll determine what t-distribution we'll be working with. It'll be based on the sample size. And so we'll talk about the degrees of freedom for the t-distribution, and that's just always one less than the sample size. Okay, but we'll get there. And so, like they said, testing a claim about the population mean. And so we're going to go through sort of the, what we need to conduct a hypothesis test about the population mean. All right, so here's sort of the notation that we'll be using. A lot of this is kind of standard stuff. And if you watched my previous video, I used the symbol mu naught. Mu naught is going to be the same as mu sub x bar. I got that from a different textbook, but if that mu naught business confused you, you can just, because under the assumption of the null hypothesis, mu naught and mu sub x bar are essentially the same. But we'll go through the steps here. Okay, so again, we're dealing with the situation where the underlying parent population has a standard deviation that we do not know. And so essentially this is what we're going to use if we have a small sample type test, or if we have a larger sample size, then if we don't know what that underlying parent population standard deviation is, this will tell us what to do there. So they're giving us requirements, and of course our sample has to be a simple random sample. That's kind of obvious, but let's focus on this second requirement. So the first is, what do we have to know if we're dealing with a small type sample? This would be the small sample situation. And so a small sample situation would be like, n, I'd say less than 30. And I would say the large sample, we could include the case where n is 30. So if you're dealing with a small sample, and again, we do not know the underlying parent population standard deviation, then in order to use this t-distribution, which we're going to use and as opposed to our normal distribution, we have to know that the parent population is normally distributed. Again, that's if we're dealing with a small sample situation. So or if we're dealing with a large sample situation, then we can use the t-test, and we can assume we don't. It doesn't really matter so much whether the parent population is normal. If you're in this case over here where you're dealing with larger sample sizes, because the CLT kind of guarantees us that the CLT takes care of that. Okay. All right. So here's our test statistic. So this is going to be our test statistic. Well, they've got it right there. And so you can see it there. And you notice that we're dealing, we don't have sigma anywhere because we don't know it. But we do know the sample standard deviation. And so notice that when we use the t-statistic, we're dealing with the sample standard deviation. Because again, we don't know what sigma is. Another thing that we need to make note of again is that when you're dealing with a t-distribution, you have to know what your degrees of freedom are, and it's always the sample size minus 1. Okay, so if you're dealing with a sample of size 16, then the degrees of freedom is 15, and that's the specific t-distribution that we'll be dealing with. And if you look on your formula sheet, I believe that I do have some information about how to use TCDF, and maybe there may be another function dealing with the t-distribution. So anyway, we'll use some of those functions on our calculator here. And again, we're going to focus on the p-value approach to doing these tests. Although if you don't have the TI calculator, we may have to talk about the critical value approach. But on the test though, on the final exam, I'll make sure that if you don't have the TI calculator, then what you need will be on the will be available to you via a table. Okay, so this is just some information we've kind of talked about. So again, if you're dealing with small sample sizes, they say from 15 to 30, then in that case, you need to know that the parent population is normal or has a distribution that, according to the way they say it, that's not far from normal. And so in the problems that you'll be given where you're dealing with small sample sizes, it should tell you that the parent population follows a normal distribution. Because if you're dealing with a small sample situation and you don't know that the underlying parent population is normally distributed, then we really don't have an alternative for that situation. So that's kind of a requirement in the small sample case. Okay, well, just a couple of properties. I think I mentioned some of these, but so the t-distribution, the specific t-distribution that you work with is based on your sample size. And so remember that the degrees of freedom is n minus 1. And so the t-distribution, it is another bell-shaped distribution, so it's very similar to the standard normal. The center is 0, and t equals 0. So, before, when we talked about the standard normal distribution, it was z equals 0 was the center. So now the center, or the mean, is t equals 0. Let's see, number 4, the standard deviation of the student t distribution varies because it varies with the sample size, because you're dealing with a different t distribution if your sample size is different. So again, there's not just a t distribution, there are several t distributions. But, for a specific problem, you'll have a specific t distribution you're dealing with, and again, it's based on your sample size. Oh, and another important fact, well, maybe not so important for working problems, but just sort of for understanding's sake, is that as the degrees of freedom, if you have a t-distribution with a huge value for degrees of freedom, say like 50 or 100, then that is very, very close to a standard normal distribution. And that kind of makes sense because the sample size would be big in that case. Okay, so let's look at an example here and conduct our hypothesis test. So let's see, it says that an author obtained times of sleep for randomly selected adults, and this was from the National Health and Nutrition Examination Study. And so those times and hours are listed below. And so we're told the sample size is 12. So let me stop right there and make note that the degrees of freedom for the underlying t-distribution will be 11 for the t-distribution. So that kind of tells us, that tells us exactly which t-distribution we'll be working with. So we'll be dealing with a t-distribution with 11 degrees of freedom. All right, and so also we're told what the sample mean is and the sample standard deviation. Okay, so a common recommendation is that adults should sleep between 7 and 10 hours each night. And so we're going to use the p-value method with our alpha is 0.05. That's our significance level. And we're going to test the claim that the mean amount of sleep for adults is less than 7 hours. Oops. Okay, so we kind of need to understand what is our unknown here. What's the parameter that we're dealing with? So the unknown here is mu, and that is the true mean amount of sleep for adults. So that's our unknown. And so let's see. The claim, we're testing the claim that the mean amount of sleep for adults is less than 7 hours. So the suspicion is that basically that adults don't get enough sleep, which I would probably believe that to be true. So here's our data. And so the question is, does this data support the claim, the alternative here? Well, this will show up in our alternative hypothesis. So is mu actually less than 7 is essentially what our alternative hypothesis will be. So our the null hypothesis here would be that mu is equal to 7. Technically, it's that it's bigger than or equal to 7, but for the null, we always give that an equal sign. And so that's sort of the default belief at this point. And so really the whole purpose for the test typically shows up in the alternative. And the alternative is that the true mean amount of sleep for adults is actually less than 7. And so we want to determine, does our sample data support, does it support the alternative, and do we have enough evidence to reject the null hypothesis, or is it true that our sample results are not contrary enough to the null so that we can reject the null hypothesis? Okay, so that's our null and our alternative. And let's see if they did that for us. Well, a couple of checks. Well, when you're given a problem, it'll be a simple random sample. And so the second question is the population normally distributed? Because we're sort of dealing with a small sample kind of situation. Well, let's see, were we told that? Oh, we haven't talked about this, but they're using a normal quantile plot, and again, we haven't talked about this. So, in a problem that we would be given, then somewhere in the text, it would tell you that to assume that this data comes from a normal population. So let me just add that here. So we're assuming this data comes from a normal population. But let me just talk a little bit about the plot that they have to verify that that the data does reasonably come from a normal distribution. So you see this normal quantile plot. If, and this is something that you would have to have technology sort of to generate, but basically what they've done is they've recorded the data and compared it to the percentiles that you would expect using a normal distribution. Okay, so to make a long story short, notice how this data conforms pretty well to a linear sort of pattern. That data conforms nicely to a linear type shape, and so pictorially that will kind of tell you that it is reasonable to assume that this data comes from a normal population. Okay, so but again, for the problems that we'll do, particularly for test questions, I'm going to make sure that it tells you whether if the data comes from a normal population or not. So this would be part of the text there. And again, the reason why we have to be concerned with that is because we are dealing with a small sample size. We're dealing with just a sample of size 12. Okay, so that's that. And this is just setting up our null hypothesis and alternative hypothesis. And we did that before, that's correct. Okay. We know that our alpha was given as 0.05. And so the sample statistic that we'll use is the t-statistic. And again, the clincher here is that we do not know the underlying parent population standard deviation. So we don't know what sigma is. So we're using a t-distribution. Okay, so if we plug in everything that we were given, then we'll use here's the formula for the test statistic. In this case, it is a t-statistic. And so this mu sub x bar, this 7, that in the previous video I call that mu naught. That's the number that comes from that's the number that shows up in the null hypothesis. So this is the number that shows up in H naught. Remember that was 7. Because remember that when we conduct a hypothesis test, we operate under the assumption that the null hypothesis is true. So if the null hypothesis is true, then the mean of your x bar would be 7. Okay? So, all right, so we got a t-value of negative 0.290. So how do we get the p-value that goes along with this? Well, the first thing we need to do is go back and look at the alternative hypothesis. The alternative hypothesis is that mu is less than 7, and they use a subscript of 1, and I use the a. It's either way, it's the same. So since the alternative hypothesis is that mu is less than 7, this is what we call a left left-tailed test. And so our p-value area is going to look something like this. And if you want to, you can kind of use the less than symbol as sort of a memory or a mnemonic to tell you where do I shade in to find this p-value. Well, just imagine that as like a pointer to the left. And that'll help you to sort of remember that, okay, I shade in the left tail area. And if we had had mu bigger than 7 in our alternative, which of course we didn't, but if this had occurred, then that greater than, you can think about that as an arrow pointing to the right. So the arrow, the greater than or the less than symbol will kind of help you to determine, what do I shade in, what area am I looking for to get my p-value. And so let me scratch that out because that's not really what we have. Okay, so the p-value would be the area under the t. So we're dealing with a t here. And so negative 0.290. And whatever that area is, that's our p-value. Okay, so in the calculator, we're going to go to second distributions. And you should see t-CDF. All right, and so we're going to go there. And so the first value that we'll put in is negative infinity because we're looking at this left tail area. So negative infinity, that's -1, and then the E99, and then a comma, and then we're going to stop at the negative 0.290. And then the last parameter that you have to put in is you have to tell your calculator which t-distribution are we working with. And the way you tell it that is you have to give it the degrees of freedom. And remember that the degrees of freedom in this case is 11 because the sample size is 12. And so you just do one less than that. So that's the last parameter that you put in. And then that will give us a p-value of about 0.389. And let me just double check with what they have to see. Yeah, so they use technology to do this, and you can see the p-value right there, 0.389. Well, remember that the rule is, because we're sort of getting to the point to where we're going to make a decision about this hypothesis test. And remember that so we're trying to decide, can we reject the null hypothesis? And we only reject if we have small p-values. And how small is small enough? Well, you have to look at your alpha value to determine that. But in this case, that p-value is nowhere near being small enough. Because remember, what does the p-value measure? It measures if the null hypothesis is true, how unlikely are these sample results that I observed. And so in this case, that p-value is telling us that those sample results are not that unlikely. So in this case, I think our decision is going to be to fail to reject. Our decision would be to fail to reject the null. So we don't have enough evidence to support the alternative. Yeah, so we fail to reject the null hypothesis. And so step 8, they give us a nice summary there. Because we fail to reject, then we conclude that there is not sufficient evidence to support the alternative, to support the claim that the mean amount of adult sleep is less than 7 hours. Okay, I kind of would have thought that we would have rejected the null, but apparently what we observed from the sample is just not support the alternative enough. Okay. All right, well, the details are in the slides. We'll stop this video for now, and I may post one more video just to get some more practice with these hypothesis tests.